So this is a piecewise defined function where within the domain from negative infinity to -2, it's following the graph that is drawn here, but then it changes to another function at -2. The filled in point that you see here means that that point is included in the function. Or in this case, we're still calling it a relation. This is an open circle, so that means that that point is not included, but right after that point, the graph begins. So what you want to see on this graph is if I said this is the function f of x, if I asked you what f of -2 is, you would tell me this y value here, -2. If I asked you what f of 4 is, you would have to say that it is undefined because it doesn't have a closed circle on either of these two places. So to be a function, the answer to each of these outputs for any x coordinate is either one single answer or undefined, and then it's still a function. Did that bring up enough to remind you of the piecewise defined functions? And anytime you run into a question, make sure you let me know. So, is there a vertical line that I can draw that goes through this function more than one time? A vertical line. So I'm going to attempt to draw a vertical line with this program. Let's see how well it's going to work out for me. Okay, that's pretty good. So what I'm going to do is I'm going to move this vertical line along. And is it crossing through only one point? Or is it crossing through the graph only once? If I'm able to actually put it on -2, it only crosses the graph at that dot right here. At x equals 4, it does not actually cross through the function. Right now, where you see the line, it's crossing through the graph only once. If I bring it over here, it's only crossing through it once. Here, it's only crossing through it once. So do you see that there are no vertical lines that will cross through it more than one time? So that makes it a function. Anytime you have a graph on the XY plane and you are asked if it is a function or not, what I just described is the test you want to use. For any vertical line that you draw, if you can draw a vertical line that crosses it more than once, it is not a function. But if every vertical line you can possibly draw can only go through it one time or never goes through it, then it is a function. For a table of values, that's actually easier. Look in your input column. Do you have anything repeated? Are any of these inputs repeated? Then if none of them are repeated, then that means for each one input, you're only getting one answer out. Now, what would it look like if it was not a function?
I don't think it is a function. There's another 5 at the end.
That's actually really important. And what I'm going to do is I'm going to do a real quick kind of plot. What?
Oh, with the vertex and then it goes.
Yeah, it's an issue of the outputs are allowed to occur more than once, but how should I, let me be careful how I'm saying this. Hold on a second. Let me think about my words. What I'm going to do is I'm going to approxiplot these points. I have input 12, output 5, input 7, output 9, input 4, output 5, and I'm starting to lose my place now. 5 was there. There we go. These 2 points are at the same y level. One of them is 4 for the x, the other one is 12 for the x. And then I can continue plotting the other points, -3, -2. I'm just going to guess to plot. And then 9, -1 is not quite as far down. The idea of being a function is vertical lines only go through one point. And this happens, that any vertical line goes through only one point. Having these 5s right here is having a horizontal line go through more than one of them. But that's a different test. That's to determine if the inverse of that relation is a function. But to determine if what is there is a function or not, it's that every input that you have gets only one answer. So what I need to show you is an example of what I would need to add on to make this not a function. First, I'm going to answer that this is a function. And now I'm going to change it. And it's very important that I say I am changing this function that I'm working with. I'm going to erase what I drew down here. And I'm going to add another line on. This would not be a function because the input number of 7 has 2 different outputs. So if I were looking at this visually, when I find x coordinate 7, there are actually 2 points at x equals 7. That causes me to be able to draw a vertical line that goes through more than one of those points. So again, to be a function, every input only has one output. Now, I want to say this. If this was the table that I gave you, this actually would still be a function, but it's a table with that repeats itself. It's redundant. It wrote one line that just really confuses you because it's repeating something that's already known. So it's actually more confusing the way that is written. But I want to emphasize that if you have the same input showing up twice, it has to have different outputs to be a problem with calling it a function. It has to have different outputs for one input to be not a function. So I'm hoping that that clarifies the table for you. Now, with solving the equations, I'm going to go through this quickly due to time. And stay with me as much as you can because I need to slow down on the problems that come after this. When you're solving equations, you're looking for the weakest PERMDAS operation. You understand that when you see a root, there's a parentheses around everything inside that root, making that super strong. The weakest link here is the addition of 6 outside the square root. So the first thing I do is subtract 6 from both sides. Then I want to realize again still that this is a parentheses. The root 3, which is at the same level as exponents, is a weaker operation than parentheses. How do I undo a cube root? What is the opposite operation of cube root?
Cubing.
You got it. So you want to do the opposite operation, cube both sides. That will cause these operations to cancel. And when those cancel, you have just that 2x minus 1 that was in a parentheses, but now that's all you have is the parentheses, so you don't need it. And then 2 multiplied 3 times is what number?
8.
Thank you. Also, if you're able to have your webcam on, you need to have your webcam on. People have let me know if they're not able to have their webcam on, and I'm fine with that. But if you're able to, I need to be able to see that you're actually there and not somewhere else, and you're not at your refrigerator, shall we say. Because I think if I were wandering during class and didn't want to attend, my refrigerator would be where I'd want to be. But we all have our places. Anyway, now this one is pretty straightforward. Add 1 and then divide by 2. Over here on number 5, the addition of 8 is the weakest operation, so I first subtract 8 from both sides. Then I will have 27. And now I need to undo cube with its opposite operation, cube root. That causes these to cancel. And then when you're taking a cube root, you're asking what number can I multiply 3 times to get that?
3.
Oh, you'd be at your coffee machine. Well, I guess I'm not going to my coffee machine because I've already got my coffee right here. Then subtract 4, and we have a solution. So what I wanted to focus on with this in the classwork, and it's going to show up in homework, is being able to solve equations with cube roots and cubes using each other as opposites to undo each other. Now, this is really an issue that's more about understanding the notation and what they mean. You've seen functions written in this manner before. And I want to emphasize to you because I've seen it be a problem before. When you see this letter and then the parentheses and this variable in here, that is not a multiplication. This is giving you a name of a function. This is telling you who the input variable is. And writing f of x is essentially the same thing as writing y instead of it. It's just when you write it this way using function notation, it allows you to, first of all, name that particular y versus this other y function versus this other y function. So now we name them so we can talk about function f, function g, function h instead of the first function I drew. But it also explains to you who the input variable is. And right now we're just using the x variable as the input. So what you want to know is, for number 6, this is asking you if 10 is the x, what is the y? When you read these, you literally just need to find the function with that name and replace whatever is here into its x. And that is all you are expected to do. You want to know that in number 7, when it says g of a plus b, what they're wanting you to do is go over to the g function. I'm going to erase all this excess so we can focus on that. So I've got the name of my function is g. The input is going to be a plus b. So when the function is defined, it is defined as 5 times input minus 12. You're going to do 5 times minus 12, and then whatever is in there, you're just going to put it in. That, and again, I want to say what these problems are here for is to make sure you understand the language that is being used and know what they are asking you to do. This can be minorly simplified to distribute the 5 over the addition, but there's really not much that can be done beyond that. For number 8, you want to see that you have this multiplication. That multiplication takes place after you have found out what h of negative 2 actually is. So we're going to find what is h of negative 2. And I'm going to just write it separately. H of negative 2 is whatever my x input is, I will square it, then I will add 4 times that input, and then I will subtract 7. So I'm just taking that number, substituting it in to each x. When there's a parentheses around a negative number and it's squared, you are doing that entire negative number multiplied twice, which means 2 negatives are multiplying and you get a positive 4.
Why do you put the negative 2 in the parentheses? I got lost there.
Okay. So what you're doing is you are looking at the expression for h says x squared plus 4 times x minus 7. The easiest way to work with this, at least I have found the easiest way to work with it, is where you see an x, put a parentheses, then whatever it says in the parentheses here is going to go into each of those parentheses. If you do that, It's okay. It's just I have found that if you first write parentheses instead of the variable, and then take whatever it says here and put it in the parentheses, you save yourself on minor errors. And that makes sure that you realize that the entire -2 is squared, not just the 2. And then I have 4 times -2 gives me -8, and then -7, and then -11 if I can add on a Monday. But that was only h of -2. So number 8 was asking me to take whatever h of -2 is and then multiply it by 4. For some of you, if you're able to do this really, really quickly, feel free to do it really, really quickly. Don't feel like you have to show all of these steps that I'm showing. Okay, now the rest of what we are doing today is tricky. Listen carefully. If I'm not able to fully get through an explanation, I will continue an explanation on a recording and make sure that you have that available. And I'm going to walk you through this whole thing, even if I keep going after you leave for lunch. And you can look at the video and get that help. Now, the vertical line test was just talked about. The vertical line test determines if the graph you see is a function. So like we did earlier, if I draw a bunch of vertical lines, I can only cross this graph once. The graph is a function. The question is whether its inverse graph is a function. Remembering back to what we learned about inverse graphs, we create an inverse graph by drawing the reflection line y equals x. And then we can slowly take individual points and take each of the xy coordinates and swap them. What I'm doing right now, by the way, is not this problem and what it is asking you to do. What I'm doing is I'm trying to remind you of what you want to know as far as how to do this problem, what you want to already understand. An inverse function is found by taking every xy ordered pair and swapping the x and the y. The vertex, again, I'm still not doing the official classwork problem. The vertex has coordinates -3, 1. The inverse graph will have a vertex at 1, -3. Some points that I know are on the graph of the function include -2, 2. That means 2, -2 is a point on the inverse. This point, -4, 2, 2, -4 is a point on the inverse. Now, if you went through and you graphed the inverse function and then determined if the inverse was a function, if you drew a vertical line at x equals 2, you would see it's not a function. What you're trying to do is save your time and not have to find the entire inverse function, graph it, and then determine if that is a function. So instead of doing the work the way I just did it, I'm going to erase. To determine if a graph's inverse is a function, draw horizontal lines. If any horizontal line crosses the graph more than once, then it is not a function. Now, if you look at a bunch of horizontal lines, if I wanted to cut this graph in half so that it does have an inverse that is a function, I would include the vertex. The most common half to use is the right half, just because right we're used to more. Maybe it's because we have more right-handed people than left-handed people in the world. So the official problem of what I wanted you to see here is number 9 goes through a written out explanation of what I just said. Part A asks you to highlight a section of the graph that does pass the horizontal line test. And so there's a highlight. Now, using interval notation, what is the x interval of what was highlighted? So -3 is the edge of that highlight. And then I highlighted for where all the x values are -3 and greater. That means the x interval that I am using is -3 to infinity, including the actual x coordinate -3. Then the next question is part C. There is another section that you could have highlighted. Using interval notation, write the other x interval that you could have highlighted. So I'm going to erase what I have, and then I'm going to highlight the vertex and then just the left side alone. Now, perhaps you started by highlighting the left side, then this time you would highlight the right side. Now, the x interval where I have this highlighted is -3 for x and everything to the left of that. The interval notation that I want to use is from -infinity until I reach -3, and I include -3. So ultimately, what you need to see here is when you have a parabola, if you want to look at the inverse function, you have to restrict the domain to either the vertex x coordinate to infinity or -infinity to the vertex x coordinate. That is always what you are going to be using when you restrict the domain on a parabola so that it has an inverse function. Now I'm going to go over to where I have the answers. And I just want to point out that I wrote the 2 ways that the answer could have been highlighted at the beginning. And if you chose this one, you would have this interval in that position and -infinity to 3 in the next one. However, if this was the one you started with, then these boxes would be swapped just because of how you did it. The thing that's very important is the x coordinate of the vertex. That is always the edge of your restricted domain. The x coordinate of the vertex is always the edge of your restricted domain. Now, the next thing we are going to do is I'm going to have you sketch the inverse of a parabola, the inverse graph, but only an inverse function of it based on one of the restrictions. So what I'm having you do is rewrite the x interval that you found in part B. And then over here, rewrite what you have in part C. And I'm going to start with looking at the one I'm highlighting. If I restrict this domain to be just from -3 to infinity, then I'm pretending that all of this doesn't even exist. In fact, what might be easiest is if I actually use a white color and just kind of go, hey, it's not there. Look at that. And we are actually only looking at this half of the function that we began with. And we are drawing the graph of its inverse. Now, for the sake of having that white pen out and ready to go, for the graph on the right, if I'm using the restricted domain of -infinity to -3, then I am not using this part. Now I can nicely white it out. Maybe you want to like cross it out, whatever, but it's nice to be able to white it out. It makes it a lot easier to see what's going on. Now, we learned last week that if we want to draw the inverse, we first draw the line of reflection y equals x, or at least try to draw that line of reflection. That was a little bit better. Oh, great. That erased both of them. Yeah. Okay. And I'm going to do the same over here. Now, I have a point -3 for x, 1 for y. And there goes the rest of that neighborhood. I am going to plot the point with these reversed. So I'm going to plot the point 1, -3. Then I want to find another point on my original f of x within the restricted domain. It looks like it crosses through this point right here. So that is x coordinate -1, y coordinate 5. To plot an inverse point, I will swap its x and its y, and that's going to then be 5, -1. And you want to plot that point. And you can continue to find more points until you feel comfortable with what the graph looks like and you just draw it. I can see that I have on the original function the point x equals -2, y equals +2. If I swap those, then I'm plotting when x is 2, y is -2. And then at some point you start seeing that you can just draw basically about that. And it helps if you turn your head 45 degrees to see this blue line, the y equals x line. If you can see it vertically by tilting your head, you can see a lot better that that is a perfect reflection over that line. Then we're going to draw the inverse function based on the other restriction. Now, we do get to plot the vertex points reflection. So that was negative 3, 1. I'm going to plot 1, negative 3. And then I look for more points within the restricted domain. So I see negative 4, 2. I'm going to plot 2, negative 4. This point is negative 5, 5. I'm going to plot 5, negative 5. And once you feel like you have enough points, you can draw what you think is the correct inverse. And then again, if you tilt your head and you really look at that reflection, those are perfect reflections. So this is teaching you about restricting the domain of a parabola so that it has an inverse that is a function, and being able to look at the two of them together on one screen. Okay. Now you're going to see how it's going to be presented in your homework. That was just trying to teach you about the issues going on. You are now going to determine a first restricted domain possibility and a second restricted domain. And you can figure that out by first determining the x-coordinate of the vertex. Notice that both of these graphs are identical. The x-coordinate of the vertex is the number 2. And then you can decide which restriction you want to put in which one. So what I want you to know is when you see my work, I might have a different first and second than you, but that's just a choice as far as which one you want to do first. Let me actually do the opposite of what I have in my answer. So let me check real quick what I chose to do for my answer. I did that, so I'm going to do it the other way in class. And then you can see the two ways. So I can restrict the domain so that I go from negative infinity to the x-coordinate of the vertex. Or I can restrict the domain to start at the x-coordinate of the vertex and go to infinity. And if you read the directions, you're going to then sketch each of the two inverse functions based on the restricted domain. Now, if you have the ability to white out part of your graph, honestly, I think that is the easiest way to do this problem. So I'm going to go and blot out what isn't the restricted domain. I have my first restricted domain be negative infinity to 2. I want to keep it. I want to get rid of what isn't part of it. On the other one, I'm using 2 to infinity. I don't want to cross out 2 to infinity. I want to cross out what isn't using that domain. And now the only thing you're doing is you are drawing the graph of the inverse that is coming from the restricted domain half. So my vertex point of 2, -5 is -5, 2. I see that I have an x-intercept of 1. Or sorry, I just said that wrong. A y-intercept of -1. That means an x-intercept of -1 for its inverse. Do any of you feel like you can see the graph at this point? Keep going. Here I have -1, 4, so I'm going to draw 4, -1. And I want to make sure to clarify that this is the original. Just okay, we are now 10 minutes left in class. And I just did not change the color. Trying to get rid of that. Now, if you're starting to notice the pattern, you're drawing a half parabola, and you should see that it looks symmetric over the line y = x with only the restricted half. And then I'm going to quickly do the next one. I have 2, -5 becomes -5, 2. And then this one looks like it has an x-intercept of a little bit more than 4, so a y-intercept of a little bit more than 4 for the inverse. Yeah, it looks like I've got a point right here of 3, -4, so -4, 3. And once you feel like you've got enough points plotted, try drawing what seems to be the inverse graph and look at the line y = x. Is it a reflection? It should be. Make sure you look at the answers. I have the answers going the left and right column are swapped. And here is a nice computer-generated view of what the results look like. Okay. Now, I have a second example that I want you to try on your own, which is going to help you with your homework. The answers are right. They are posted with your classwork. And I now need to move over to number 12 here. And unfortunately, this is an issue of cutting an hour and a half down into an hour, where I can't necessarily guide you through each and every example that I would normally intend. Okay, look at the equation. Look at the equation. What is the x-coordinate of the vertex? Who's with me? What is the x-coordinate of the vertex?
2, -9.
Mm-hmm. The vertex is 2, -9. And which one is the x-coordinate? Between these two numbers, which one is the x?
2.
Good, you got it. That is the edge of your restricted domain. I have that as a first line. The edge of the restricted domain is x = 2. It's always the x-coordinate of the vertex. Then you're going to choose how your left and right columns might look different. And I'm going to, again, do it differently than I have the answers written, just for the sake of you seeing two completely correct versions. So One restricted domain is negative infinity until I reach that x coordinate 2. The other restricted domain is to start at 2 and go to infinity. Now, the answers are not going to be written until after you go through a bit of work. Watch me on this work because we're low on time. So, when I first go about finding an inverse, do you remember what the first thing was that I would do? I would put an x where there was a y and a y where there was an x. Then my job was to isolate the y. And this is the idea of just how do you solve an equation. To isolate this y, I need to undo the weakest operation, which is subtraction. Now, because of the parentheses, the next weakest operation is the squared. But do you remember that when we do a square root, we have to throw on a plus or minus sign? Now, this creates two equations. And each of these equations is going to be one of the two inverse equations. So I'm going to write this that we now have y minus 2 is either equal to the positive square root of x plus 9, or y minus 2 is equal to the negative square root of x plus 9. The quickest... What?
Don't you have to add the 2?
Yep.
You have to add 2 to that first to get the actual answer.
You got it.
Or the most.
And, it depends on if you want to write it as two equations at that point, or if you want to add 2 and then write the plus and the minus separately. It's up to you how you want to work your algebra. What I'm doing is I'm immediately writing two equations when I run into the plus or minus, but you can also do it later, and I don't have any problem with that. Now, the question, though, is which one goes to which domain or restricted domain. And the easiest way that I can explain this to you with the limited amount of time that we have is, how you think, okay, right and left. Which one do you consider positive and negative, right or left?
Right is positive, left is
Mm-hmm. Yes. So the interval that is the right interval, the one that goes starting at 2 onto positive infinity, gets the plus. So the y inverse is the positive root. And then the interval that uses the left half of your parabola gets the negative of the plus or minus. Now, I have one more example for classwork, but I only have 2 minutes left. So what I'm going to do is I'm going to talk through number 13. And while I'm going through it, class is going to end and you can feel free to leave. I'm going to continue and finish the recording. So if you need to see an explanation for number 11, I will continue recording and go over that one as well, so that I have gone through all the examples with you. And all of that you can find in Google Classroom if you go onto Google Classroom and you find classwork 1.3, right now you already have the blank copy and the answers. When I'm done recording, I'm going to add that recording into this classwork, and you'll have 3 things sitting there. And then you will turn it in on this assignment. But by doing the extra classwork examples, it's going to prepare you to better deal with homework 1.3, which you're not going to have answers for. You're going to solve some equations. You're going to try to understand within the context of a problem, a parabola. This is assumed to be review. And then what we worked on today, see if you understand the function notation, and then some problems with what we are doing now. Okay, so I am now going to begin talking through number 13. And it's 10:50, so you can either stick around and learn now or watch the video later. Okay, for the restricted domains, you want the edge. The edge is the x-coordinate of the vertex, which you can always find in the parentheses with the x. And it's honestly just the x-coordinate that makes the parentheses equal 0. So what number do I add to 4 to make 0? -4. Then you can decide what you want to be the first and the second restricted domain. It doesn't matter which order. So if I decide that I'm going to go with the left and then the right, I have my 2 restrictions. The left half of my parabola, so I'm just going to say left half and right half. Then to come up with the equations, I'm going to take my given equation, make the y an x, make the x a y. Then I'm going to isolate my y. I'm going to subtract 5 from both sides. Then when I take the square root, I do a plus or minus square root. But I just realized something. I can't take the square root of a negative number. So I have to backtrack. Before I can square root, I need to have just parentheses squared. So I'm going to multiply by -1. This is going to be easier to work with if I distribute the multiplication of the -1, where I change the subtraction order. This is going to cause the algebra to be least cumbersome. Now I can take the square root and put a plus or minus sign on. And that gives me that y plus 4 is either equal to the positive or the negative square root of 5 minus x. The last thing I'll do is subtract 4, so I'll go ahead and do that. -4 plus or minus. Now this gives me 2 versions. Y equals -4 plus the square root, and y equals -4 minus the square root. The plus will always go with the right half restriction. And the negative will always go with the left half restriction. And you don't have to show all the detailed work that I did unless you need to show it to get through the work. Do enough where you are logically making sense and doing it correctly. And I want to point out that in the classwork, I have the answers written with the left and right column reversed. So you can do it either way. One last problem. When you're looking at the graph, you're graphically looking at what is the x-coordinate of the domain, or I'm sorry, what is the x-coordinate of the vertex? The x-coordinate of the vertex is -4. That is the edge of my restricted domain. So then I have the left half, -infinity to -4. And then I have the right half would be -4 to infinity. Now, if you don't have a nice white pen, you can just cross out and it might help. -infinity to -4, I want to keep. I want to get rid of the other half. Here, I want to keep the right half, get rid of the left half. Then it's a matter of plotting the inverse points, starting with the vertex. The vertex is -4, 6. 6, -4 then is the x-coordinate of the vertex, of the inverse function. Then just take some points that you can see and plot them. So -5, +5 becomes 5. Oh, hold on. Let me say that slower. X equals -5. Y equals +5. Changes to 5 and -5. Why am I messing up? I need to write it down. I know why I messed up. I plotted a point incorrectly. I don't know if you saw. This should be 6, -4. I have found for myself that I mess up less if I write everything down. So what helps is to actually write down that that vertex was x equals -4, y equals 6. Write the reversed point and then plot it. I found one point, I wrote the reversed point, and now I'm plotting it. 5, -5. And let's see, I see another one. I see -6, 2. I'm going to write the point down. Then I'm going to reverse it. And then plot that point of 2, -6, which is right there. And after you get enough points plotted, you can draw that, and you should see that it has nice symmetry with the portion of the graph that we used for the restriction. And then we're almost done. So what I'm going to do is I'm going to write down some of the ordered pairs on the right half of the parabola, starting with the vertex. Vertex is -4, 6. I'm going to be plotting a 6, -4 vertex. I see that one of the points on the right half is x-coordinate -3, y-coordinate 5. I'm going to need to plot the point 5, -3. And then I can see here, x-coordinate -2, y-coordinate 2. I'm going to plot the reversal of those points. And usually 3 points is enough to get it going, but you can always plot more if you need to. So 6, -4, 5, -3, 2, -2. And then remember that this one was the vertex, and then you're heading toward the other ones. And then the answers show it nicely drawn by a computer. But again, you should see the symmetry with the half that was used for the restricted domain. And that's it.